This conference will now be recorded.
Very good evening.
This conference will now be recorded.
Very good evening. Today we'll be concluding this chapter by discussing some few important topics over here. So those are torque and momentum, relation between torque and moment of inertia, angular momentum and moment of inertia, and we'll see conservation of angular momentum, and finally we'll conclude with rolling motion. And if possible, we'll take some numerical example in this class. So first we'll take up the relation between torque and moment of inertia. So we have already learned that torque is the quantity or physical entity which is analogous to force in the linear motion. So this is in rotational motion, or rotation, and this in translation motion. The role played by both the quantities are the same. What do you mean by that? The meaning is that, see, if there is a particle which is having a translational motion, and if the external force F is applied on this particular particle, then it will gain an acceleration. Okay, acceleration A, and we could write this F is equal to m into A, mass times acceleration will be the external force. So similarly, in case of rotational motion, suppose torque is applied is applied applied to a body which is capable of of rotating about a fixed axis, then angular acceleration will increase, or we can say angular acceleration will be produced in the body. So this is what we have. We can say from the analogy of the force and torque. Okay, so look, in this case, suppose I want to write torque. Suppose I'll just take a rigid body, arbitrary rigid body, which has multiple number of particles, so which is constituting this rigid body. Let us say this is an axis of rotation, and from there are many particles. I'm just taking a representative particle which has mass m1 and which is at r1 distance away. So if we want to write the torque on this particle, then how we'd write? We'll be writing torque is the moment of force. So moment of force means R into F. Okay, R1 into F. F is the force acting on the particle. Okay, the external force, and which is actually create a moment or torque. All right. Now see this mass. See this force, external force also can be written as m1 into m1 into a1. This is the linear acceleration. Okay, a1 is the linear acceleration. So look, now one thing you can, okay, let me tell you this acceleration. Let us take as a alone. So m1 m1 r1 a, and see if we recollect the relation between angular acceleration and linear acceleration. Linear acceleration is equal to r alpha. So a1 I can write r1 alpha. What is this? I'll just let you know. So I was right in the beginning. So let me keep this acceleration of the particle this as a1 only. So look, a1 angular, so linear acceleration we know is equal to r into alpha. R is the distance of that particular particle from the axis of rotation, that is r1, into alpha. Alpha is what? Alpha is the angular acceleration. So alpha is angular acceleration. So this we have already learnt. Acceleration, okay. So this is angular acceleration alpha. You can be surprised to just analyze or just learn little bit here. See, a1 is the linear acceleration for this particle m1, and r1 is the distance from the axis of rotation to that particular particle, and alpha is the angular acceleration. If I want to write for another particle too, then also I can write this. See, this alpha is the angular acceleration. Since angular velocity for a rotating body omega is actually same for all the particles. Angular velocity, when you say velocity, linear velocity can be different, okay, for different particle. That depends on the position where they sit. They are sitting from the axis of rotation. Okay, I'll just clean everything and write. What I wanted to write is, see, torque is R1 F R1 M1 A1. A1 was written as R alpha. So you look, I can write M1 R1, and this can be written as again R1 alpha. Alpha is the angular velocity that does not change because angular, angular acceleration alpha. Angular velocity is same for all particles in the rigid body. So this angular acceleration will be also the same for all the particles. So I can write m1 r1 square alpha. So I would have taken this as ti, tau on the particle 1. So t1. If I, excuse me, if I calculate t2 for m2, which is at r2 distance away from the axis of rotation, t3 like that, if I calculate torque for each and every particle and then sum them up, then I get the total torque. See, I can write ti. I goes from 1 to n. Suppose there are n particles in the rigid body. So look, what I can write is, see, this means this one m1 r, sorry, m 1 or mi summation I have given already, ri square summation this into alpha. And if you recollect what is this definition, this is mr square summation of mi ri square. This gives you the moment of inertia of the rigid body, moment of inertia of the body, moment of inertia of the body about the given axis of rotation. Okay, so what is the relation we got then? Tau is equal to I into alpha. So this is the relation between torque and moment of inertia. So we can write it here. Torque is equal to tau is equal to I into alpha, that is moment of inertia into angular acceleration. Okay, this is the relation. Now similarly we will be finding out the relation between angular momentum, that is L, and torque tau. See, what is the angular momentum? Definition of the angular momentum. The definition of the angular momentum. Okay, not torque. Actually, this is I, moment of inertia. So this is angular momentum will be actually RP. Okay, I'm not writing in terms of vector notation. Otherwise, I would have written R cross P. Okay, so I'm just calculating for a single particle L1. So R1 P1. So look, this is R1, all right. What is P1? P1 is M1 V1. So look, this is actually the angular momentum of a particle which is at R1 distance having mass M1. Okay, so R1 at R1 distance. This is the axis of rotation. Okay, there are such particles, many such particles like this, and angular momentum of the first particle or particle which is having mass m1 is this one. Okay, now see this velocity v, this is a linear term. We can just convert it to angular term. Let us see what we can do. V is equal to, so okay, v is equal to r omega. We know that v is equal to r into omega. Linear velocity changes, whereas angular velocity same for all the particles in the rigid body, but linear velocity that depends on the distance where the particle is situated from the axis of rotation. So we can write here v is equal to r1 omega. Okay, not omega 1, omega, because omega is same for each and every particle. So look, if I just simplify that a little bit, what we get is this m1 r1 square into omega. Now look, if I just want to calculate torque, just summing up all of them, what I get? Sum over Li. I goes from 1 to n, small n number. Okay, so look here, this term. Okay, let us take the summation m1 r1 square. I goes from 1 to n. Okay, so this is the total angular momentum. Sorry, this is actually, yeah. So this if you just sum up, so this whole term will give you total angular momentum of the rigid body. But look, this term, this first term actually gives you moment of inertia I, as per our definition. This is mr square summation of mi ri square, and this I goes from 1 to small n. So what we have got? I omega. I'll just write it there, cleaning everything. So moment of inertia, angular momentum is L is equal to I into omega. So these are the relations. So in case of torque, we have seen tau is equal to I alpha, and in case of angular momentum, relation between angular momentum and moment of inertia is this. Okay, I omega. All right. So this thing will be applying in the next topic where it is conservation of angular momentum. Okay. So what is conservation of angular momentum? Look, we have torque, which we can write even dl dt, the time rate of change of angular momentum. This is torque, external torque. So in analogy with force, see, force is dp dt, linear acceleration, right? So if, with analogy you can understand that the torque will be also given by the time rate of change of angular momentum, not the linear momentum. Okay, so this is fine so far. So this is torque. Now look, what is this conservation of angular momentum is saying is that if the external torque, it is exactly, actually conservation law is exactly equal, exactly same for linear or translation motion also. See, if force, external force is zero, then what will happen? The total momentum will be conserved. Okay, so in this case, if the torque, external torque is zero, then what will happen? If the external torque is zero, we'll see what is happening. So if the external torque is zero, then angular momentum remains constant. Okay, so the total external torque acting on a body is zero, then the angular momentum of the body is conserved. So this is called conservation law. So I'll write it what I said. So if the external torque, this is zero, that means this is the zero, then see, this implies dl dt. If this is zero, so this must be a constant quantity, so which gives you L is equal to constant. So if this is the thing, then we can write from our previous slide. See, angular momentum conserved means, suppose in the motion, rotational motion, in the beginning of the rotational motion, suppose the angular momentum was L1, and at the end of the motion is L2. Okay, then according to law of conservation of angular momentum, they must be remaining conserved, so, or constant. So this L1 is equal to Lt. So if this is initial and this is final, so initial angular momentum will be exactly equal to the final angular momentum. Okay, this is the statement. Now what we'll do, we will see nice applications of this conservation of angular momentum. So L, we know L is equal to I omega. So we can write L1 is equal to L2, which implies that we can write I1 omega 1 is equal to I2 omega 2. So you might be surprised, what is this omega 1 and omega 2, etc. See, as I said, you suppose in the beginning of the rotation of the rigid body, angular momentum is I1 and angular velocity is omega 1, then this will give you the initial torque, sorry, initial angular momentum L1, and this is I2 into omega 2. This will give you the final angular momentum. Okay, so according to conservation of angular momentum, what we have got, this this is important. So this will have external, sorry, it will have practical example, like practical applications. See, in this figure, as you can see, divers, okay, divers, what they do, they actually jump from a spring plate. Okay, spring plate. And see, when they jump on the spring plate, they will be actually getting an upward motion. Okay, upward motion. And then see what this diver does, they just sometime they, for some time, like they stretches their legs, or sometimes they can pull their legs and hands towards his chest. So by that, what can be done from this formula, you can understand that if I1 is more, then omega 1 will be less. Or in reverse way also, if omega 1 is more, then I1 will be less. What does it mean? It means that by changing the moment of inertia, you can control the angular velocity. By changing the angular, sorry, by changing the moment of inertia, we can change the angular momentum. Okay, and by changing the angular momentum of 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 particular body, we can change the, directly we are changing the velocity, angular velocity. Okay, I'll just explain it with this figure. See, skydivers, sorry, this divers, like actually swimmers, so they do certain activities with this, like in the principle, on the basis of this principle, conservation of angular momentum. Initially, when they jump off from the spring plate, they actually pull their hands and legs inward, so that so that their sorry, moment of inertia will be less. Suppose if a person is stretching his legs and hands, then about an arbitrary axis of rotation, the moment of inertia will be more, because their hands and legs are away from the axis of rotation. So overall, the body will have more moment of inertia. If this is more, if this is more, okay, this is, suppose I1 is more than some initial value, then what happens? To make the angular momentum conserve, see, L is equal to I omega. To make the angular momentum conserve, if this is increasing, then this must be decreasing. So angular velocity will be decreasing. Okay. If, sorry, if they pull their hands and legs inward, then it will decrease actually. Okay. Angular momentum will be, sorry, moment of inertia will be decreasing. Okay. If this decreases, then this will increase. So they will actually rotate very fast, as you can see, and top here and here, they will be rotating very fast with greater angular velocity. But as soon as they are just coming, suppose this is the surface of the water where they will be actually reaching now. So when they are almost going to reach the water surface, so their angular velocity has to be decreased. Okay, suppose this is omega 1 and this is here omega 2. This has to be decreased. So what you have to do? So here moment of inertia was I1, here moment of inertia I2. So if you have to have omega 2 less than omega 1, you must be having I1 less than I2. Okay, if I2 is more, then the product I into omega, this will be conserved if this omega 2, that means angular velocity, decreases. Okay, so that's how they reach to the water surface, and go into the water very smoothly. You can watch some YouTube video also maybe on this particular example. Another example I can give you, suppose there is a turntable, a person is doing such an exercise. So they see this person has two dumbbells in his hands of same weight, suppose. So see, I know this is the case. So suppose this is I1 omega 1, this is the L1 angular momentum, and this is L2 is equal to I2 omega 2. So this both has to be same actually. L1 and L2 remains conserved because the person on the turntable is not experiencing any external torque. So angular momentum will be constant. That means L1 will be is equal to L2. All right. So in this case, see what happens. You might be able to see some activities kind of this in uh, acrobats. Some acrobats also do like do this kind of things by the use of this conservation of angular momentum principle. So look what happens. So when the person is sitting on the turntable, he is rotating about this axis, passing through his middle of the body. Maybe you can see that, and see when the person keeps his hand and legs little bit stretched, then what happens? The moment of inertia of the person along with these dumbbells will be more. That here it is actually more than I2. The condition is here. You look, I2 is the moment of inertia when the person is pulling his hands with the along with the dumbbell. Then see the the moment of inertia I2 is actually becoming lesser than I1. So in this case, when the moment of inertia is more, the angular velocity will be less. So the person will rotate very slowly. If he wants to increase the speed, then draw he has to draw his hands along with the loads towards his chest, so that this moment of inertia will be less than earlier, and the angular velocity increases. So this is how the angular velocity can be controlled by this person himself. Okay. So this was another example. There are many examples where the application of conservation of angular momentum has been done. So this is actually ballot dancer. So this figure is for ballot dancers. So what they do actually, they skates on the ice. So sometime they have to control their motion by stretching their hands and legs or bringing them near her body. In this case, you look. So when suppose the arbitrary axis of rotation is this, when she stretches her hands and legs, what happens? Moment of inertia anyway increases. Okay, here moment of inertia increases. So because of that, the angular velocity will be decreasing. But when she wants to increase her speed, angular speed, then she will be slowly stretching her legs and sorry, pulling her legs and hands towards her another leg, so that as a whole the moment of inertia I2 will be lesser than the previous value. So angular velocity will be increasing. So this is how we can use this thing. I1 is I1 sorry I1 omega 1 is equal to I2 omega 2. Okay, this is the formula for angular momentum conservation. Okay, now we'll see one numerical example of this particular principle. I'll just write the problem and then we'll discuss this problem how to solve. to solve it. The problem is, suppose a horizontal disk, horizontal disk sorry, this is C. Horizontal disk rotating about is rotating about a vertical axis passing through its center of mass. Its center of mass makes, okay, so it makes 180 rpm initially, okay, rpm. A small piece of wax, a small piece of wax of suppose 10 gram falls on the disc at 8 centimeter from its axis of rotation. Its axis of rotation. If the frequency, question is if the frequency, if the frequency, if the frequency is reduced to 150 rpm, calculate the moment of inertia of the disk. So this is the question. I'll just explain the question first, then I'll solve it. Suppose horizontal disk is rotating about a vertical axis passing through its center of mass. It makes 180 rpm. A small piece of wax of 10 gram falls on the disk at 8 centimeter from its axis of rotation. So if the frequency is reduced to 150 rpm, calculate the moment of inertia of the disk. Okay, I'll just go to the next slide maybe. Okay, this is, okay, let me do the problem here, solve the problem over here. So look, I'll just draw the situation first. So this is a disk, not this one. I am solving the problem. So this is a disk which is rotating with rpm given. So that is, okay, so this is not the angular velocity. We have to find out what is the angular velocity. So that was, so frequency given in, see, 180 rpm. This actually from here you will be able to get omega 1. Okay, initially about the axis which is passing through its center of mass. I'm just taking normal to it. and see some drops of, okay, a piece of wax is like has fallen on the disk, rotating disk, at a distance 8 centimeter from the axis of rotation. Okay, and this has mass 10 gram. You have to find out what is the moment of inertia. So if the final after just wax being pasted on the disk, the angular velocity decreases. That's why this becomes the RPM 150 RPM of the disk now. So we have to find out what is the moment of inertia of the disk, okay, about its center of mass. So that is the problem. Look here, we have to use the parallel axis theorem. We know parallel axis theorem, moment of inertia about any axis, given axis, is equal to the moment of inertia about the center of mass of the body, rigid body, and this is the and multiply and summation of multiplication of the mass of the mass of particular particle about a given about a given axis. This one, m into r square. This is the product of the mass of the particle, and this is r square. There is the square of the distance from the axis of rotation. So this gives you the total moment of inertia. Okay, look what is given is here. RPM changes because of this wax. So what is RPM? RPM means revolutions per minute. So if you want to find out omega from here, so omega means actually 2 pi f. 2 pi f is the angular. So 2 pi into f. F is the frequency. We have to find out what is frequency. Frequency actually 2 pi f into RPM is this time, this much time. Sorry, this 180 RPM. You have to make it RPS. So if this is in minute, you have to make it in second. So you have to divide with 60. So this will give you radian. So look, this will be actually 6 pi radian, and similarly this omega 2, or the final angular velocity, will be 2 pi f2, 2 into pi. So f2 is the frequency I have to calculate per second. Okay, so this is actually 5 pi. Okay, this is 5 pi. Now what you should be doing, 5 pi, this is radian. You have to use the conservation of angular momentum. Okay, so suppose in the beginning when the wax was not pasted with the disk, it was rotating about the center of mass, and that if I take as ICM, okay, I can write this as ICM into omega 1 is equal to I, now the moment of inertia, into this. So this is the moment of inertia, total moment of inertia now. Okay, so total moment of inertia means moment of inertia about center of mass into the plus mass time square of the distance between the particle and the axis of rotation. So if this is the case, then we can actually write down this I as ICM plus m r square. So ICM is how much? So that is the thing we have to find out. And see, from here we can actually, from using this, actually we can find out what is I. Let us do that. What is I? I will be I1 omega 1 divided by omega 2. So I1, we know I1 is actually ICM, and omega 1 is actually 6 pi, divided by this is 5 pi. Okay, we know this. Pi goes off. Let us keep this as 6 by 5 itself. 6 by 5 ICM. Okay, ICM. Now if we put it here in the formula which we know from parallel access theorem, so according to parallel access theorem also we can find out I is equal to ICM plus m into r square. So this m, okay, let us write then what is ICM, or let me write this I is equal to 6 by 5 ICM. Okay, and this is ICM, another ICM, and here m is 10 gram, this is 10 to the power minus 3 into 8 into 10 to the power minus 2 whole square. Okay, so from here if we calculate, so this will be ICM by 5. If we just take it here, so it will be ICM by 5 into 10 into 10 to the power 10 into 64 into this is 4, this is 3, so 10 to the power minus 7. And from here I can find out what is ICM. So 5 into 10 into 64 into 10 to the power minus 7. So this will give you the moment of inertia. Okay, so this will give you moment of inertia. So it will be almost, so nearly equal to 3.2 into 10 to the power minus 8 kg meter square. Okay, kg into meter square. So this will be the moment of inertia of the disk, original disk. I hope you have understood. I'll just repeat it once what I have done. See, I have just used the parallel access theorem. So parallel access theorem is that the moment of inertia of any object about an arbitrary axis can be obtained. Actually, if that arbitrary axis is parallel to the axis passing through the center of mass or maybe any other axis, then the moment of inertia of a particular particle or object about that particular axis is equal to the moment of inertia about the parallel axis. It may be center of mass, like axis passing through center of mass, or maybe diameter also, as you have done in case of previous classes, like in case of disk or ring we had done already. And this is the mass times the square of the distance between the parallel axis. We have used that only. See, IB, that is the arbitrary axis. Okay, I about B. So now again we know that the reason for this frequency to be reduced in this case is that the moment of inertia changes. So disk has its own moment of inertia about rotational axis. When the wax drops on that disk, the whole moment of inertia of that particular system will be different. Okay, so that is what we will be able to find out using parallel access theorem. And to find out the value of ICM, will be actually getting the moment of inertia I or I2. Okay, this we know already. we can calculate from here I1 omega 1 is equal to I2 omega 2, and omega 2 we know what is omega. Omega is the angular velocity that can be obtained to pi f, and rpm actually this is the frequency in minute, not in second. Frequency means revolutions per second, so that's why you have to always, so whenever there is rpm you have to divide that with 60, then you will get rps, so that is rps. Okay, so you have to divide with 60 into 2 pi multiply, so that will give you the rps. Okay, so this is how you have to solve the problem. Now we'll just go to rolling motion. Okay, so rolling motion, this motion is very common, and in our day-to-day life we know this motion very well. See, suppose you are riding a cycle, you are riding a bike, or maybe any vehicle which is having a wheel. So rolling motion actually is being observed in those vehicles, any vehicle which has round wheels. And if I tell you what is the rolling motion, you can just imagine how your cycle, like wheel of your bicycle, moves forward. What it does, actually it rotates as well as it translates. So it has actually two motions. One is rotational, another one is translational motion. So according to definition, rolling motion can be considered as the combination of pure translation and pure rotational motion. Pure translation and pure rotational. Okay, so that is the definition of rolling motion. Okay, now rolling motion, there are actually two conditions. Motion, rolling motion without slipping. So suppose in this case you look, if I just take this particular case, okay, let me just take this one. So this is the first position of the wheel, suppose, or disc, maybe let us say disc. See, whenever this disc is rotating, the center of mass, when a translation motion actually is being described by the motion of the center of mass of the wheel or the disc. And see, so the body, this whole wheel has the velocity same as the velocity of the center of mass. So in the forward direction, which is parallel to the plane of the motion, there will be translational motion of the center of mass, that is VCM. Okay, and when it rotates, you just think that each time some or the other point which is in contact with the ground will be at rest, and that is the actually fixed axis, like that is the instantaneous axis of rotation. That is the instantaneous axis of rotation. That axis of rotation changes time to time. When it was here, this point was at contact, so this is suppose rotating in this way, in, okay, this was in contact, and this contact point will be always remaining fixed. This is the this will be actually motionless or at rest. So this is the condition for rolling, like rolling motion without slipping. So rolling motion is actually combination of pure translation. Translation pure means what? There is no slipping and all. Translation plus pure rotation. Okay. And in this case, we will just do one set of like understanding here, some understandings about translational motion and rotational motion. So in case of translational motion, the velocity of the whole disk will be actually the velocity of the center of mass, as I was saying. And suppose the center of mass has velocity vcm. Okay. Now, if I just consider any particle over here, any particle at this particular position P, I have to calculate what is the velocity of this particle or this particle or this particle, that particle. Every particle we can find out the velocity, linear velocity. Obviously, for translational motion, we will be talking about linear velocity, and linear velocity is actually not constant velocity. It changes with the distance of the particle with respect to the axis of rotation. So for that, suppose this is the axis of rotation here, and this is the particle which has two motions, because this disk has two motion. One is translation, which is vcm in this direction. Another one has rotational motion, and this rotational motion, suppose this is this. Okay, this is the rotational motion. So what will be the resultant? It will be this one. Okay, this will be vp. This is v rotational. And in case of v rotational, so this point will be fixed. So v rotational pure, like without slipping, v rotational will be always is equal to v is equal to r omega. Okay, r omega. V rotational will be r omega if this is pure rotation. Okay, so this disk has translational motion due to two things. One is due to the translation of center of mass. Okay, and it has another component of velocity which is coming from the rotation, pure rotation of the disk. So that's why this is linear velocity, but it is coming due to rotation. So I have got two translational motion vcm. Okay, vcm, and another one is rotation, translational motion or velocity, translational velocity due to rotation. These two things are there. Okay, and the resultant will be obtained from the, yeah, by the use of vector notation. If you write, so vp will be actually vcm yes, so you can see from here, so this is vcm plus v rotation. Okay, v rotation. So from this we will be able to get the total translational motion or translational velocity of any particle on the disk at any instant of time. Okay, all right. Now we'll we'll see how rotational motion is being conducted here in this rolling motion. Let me clean everything. So if the disk is rotating with angular velocity omega, suppose this disk is rotating with angular velocity omega about its symmetric axis, that is suppose passing through center of mass, the linear velocity of the particle p at a distance r, okay, this we have already discussed. Anyway, so we have seen that v rotational will be r omega if this is r. Okay, this is the axis of rotation. Anyway, now effective linear velocity, as I told you, so that will be the thing. Now the instantaneously, in each case, if this point of contacts are at rest, then that motion will be called as rolling without slipping. Rolling without slipping. Without slipping. Without slipping. Okay. rolling without slipping. So what is the condition? Condition is VCM has to be is equal to R omega, because see, when we have, okay, so this is the thing. This is the condition for rolling without slipping. VCM, center of mass, linear velocity of the center of mass has to be equal to R omega, that is the translational motion due to rotation at any instant of time. Okay, now we'll find out velocity for this point and this bottom point. So let me write it here. Velocity of the top point and velocity of the bottom point. So velocity of the top point, what you get here, so you will get R omega due to rotation, and you will get VCM. And obviously, if this rotation is without slipping, then VCM also will be R omega, or in other words, so it will be 2 R omega, or from here we can write that R omega is equal to VCM. So if you write that, then it will be 2 VCM. Okay, so top point will be having this much velocity, and what about the bottom? Bottom point will be having velocity 0. As we know, instantaneous velocity will be 0. What about the center of mass? So center of mass will be velocity, having velocity VCM only. Okay, so sometime you will be asked to find out various quantities in this rotational motion using, like they will say, uh, rolling without slipping. Without slipping means V is equal to R omega. That condition you have to use. Okay, and you have to find out what are the velocities of the top point and velocities of the bottom points, velocity of the center of mass. I'll just briefly repeat this particular case, and then I'll stop today's class. And there is one special case, rolling motion along an inclined plane, that I'll take in the next class, because this, if I start, it will take long time, and there are many good corollaries from this particular concept, rolling motion along inclined plane, that will take up, okay, in the next class. So let me just repeat this particular rolling motion. Like, see, rolling is combination of translation and rotation. So how translational motion, or translational, what are the translational velocities, and rotational velocities of various points, how we calculate. See, the translational velocity of the disk can be given by the velocity of the center of mass itself, because we have seen that rigid body, the motion of the rigid body can be expressed by the motion of the center of mass. That is what we have learned in the beginning itself. So if VCM of, like, VCM is the translational velocity of the center of mass, then that will be the velocity of the disk, whole disk, and that velocity is parallel to the plane. You can see that. And in this case, since it is rotating, actually I just forgot to tell you, in case of rotation, that actually if this point is moving this way, so this bottom point will move in the opposite direction. Okay, all right. So actually this, okay, let me tell you. At the bottom point B, the linear velocity will be due to rotation, and that is directly opposite to the, okay, so instantaneously it will be at rest, that means translational motion will be 0, but there will be rotational motion for this bottom point. This is B, this is A, okay, and this is suppose C. So these 2 points will be having equal and opposite velocity. So V rotational in this direction, V rotational will act in this direction. Okay, they will be exactly in the opposite direction. And for rolling without slipping will be Vcm is equal to r omega. And see, velocity, translational velocity due to rotation will be occurring as V rotation is equal to r omega. Okay, so instantaneously the bottom point will be at rest if Vcm becomes is equal to r omega. So this is called the condition for rolling motion without slipping. Okay. All right. So we'll stop it here for today. We'll take up then next. I think this topic is very simple, but there are various numerical examples on this particular thing, like inclined plane. Okay, so motion in a rolling motion in a rolling motion in an inclined plane. So what I'll do in the next class, I'll take up this particular topic and I'll take up numerical examples for all over the chapters, the overall chapter, and then conclude the chapter system of particles and rotational motion. Okay, so bye for today.